All right, last week we finished up by talking about the role of the nucleophile in SN1 and SN2 reactions. And we said in an SN1 reaction, the nucleophile doesn't really matter that much because we're going through a carbocation intermediate that's relatively unstable. And so you can use a weak nucleophile that's not even charged. You can have a neutral nucleophile. And in the top example, we had water. And then we said for SN2 reactions, the nucleophile really does matter because the nucleophile is going to be attacking your electrophile. If you're using a weak nucleophile, it's not going to attack as aggressively, and it's not going to favor the SN2 reaction. We're going to talk more about the comparative ranking of nucleophiles here in a minute, but the ranking between various nucleophiles really comes down to a stability issue. An unstable nucleophile is going to react at a faster rate. And so we're going to cover what we can use to destabilize our nucleophiles in favor reactions. The last little bit we talked about was the size of our nucleophile. We said that big, bulky nucleophiles generally aren't as good as smaller, less hindered nucleophiles. So we were comparing a tert-butyl group to an ethyl group. Obviously, a tert-butyl group takes up a lot more room because of those two additional methyl groups dangling off of it. But let's kind of make a summary here. First thing is that less stable nucleophiles are more nucleophilic. The second one we said was that less bulky nucleophiles are more nucleophilic. And the last thing I really wanted to drive home is that nucleophile strength is directly related to activation energy. If you've got a really large activation energy, does that mean you have a good nucleophile? No, you want a relatively small activation energy because you're relying on your nucleophile running into your electrophile. You don't want that to be energetically unfavorable. Students oftentimes get this confused because they think about delta G. We're not concerned with delta G. We're concerned with activation energy. So we're not looking at the Gibbs free energy change for the reaction. Let's compare nucleophilic atoms in the same row. Okay? So a little bit like we did with bases where we compared atoms in the same row. Let's do hydroxide versus amide, which is NH2 minus. Which one do you think is going to be more nucleophilic and why? Which one's less stable? We got to go back to our acids and base stability comparison, right? If we're looking at conjugate bases and comparing these as conjugate bases, which one's more stable? Hydroxide, right? Hydroxide's more electronegative than the nitrogen and the amide. Therefore, it's okay with the negative charge, where nitrogen really isn't that electronegative compared to oxygen, so it's unhappy. So we can look at this and we can say NH2 is less stable since N is less electronegative than oxygen. Therefore, do you think this is going to be more or less nucleophilic? More nucleophilic. Come on. All right. So if we were doing a competitive SN2 reaction where we had both reactions running, but one was with hydroxide and one was with amide, the one with the faster rate would be the one with amide, right? It's got the lower activation energy. The rate will proceed faster. Let's do a different comparison. Closely related. Let's do water versus ammonia. Ooh, which one's less stable? We're more willing to participate in a nucleophilic attack. Oh man, this is a little bit tricky. It's not directly related to basicity. Basicity is looking at Gibbs free energy change. We're looking at activation energy. Think about the lone pairs on these. Which lone pair is being held more closely? The lone pair on oxygen or the lone pair on nitrogen? Oxygen. Oxygen's very electronegative, so it's going to hold on to its lone pair tightly. That lone pair is going to be close to the nucleus. The nitrogen lone pair is going to be further away and more accessible to participate in a nucleophilic attack. So the same trend holds. We can go and we can say, all right, the lone pair is held less tightly. Therefore, it's more nucleophilic. If you think about water, those lone pairs are held really close to the nucleus because oxygen's so electronegative, it's really greedy. Therefore, the lone pair can't really reach out and participate in a nucleophilic attack as easily. All right, let's compare another one. Let's compare water versus hydroxide. Which one's going to be more nucleophilic? Which one? Yeah, hydroxide, right? That seems pretty apparent because it's got a negative charge, it's less stable. So we can go through and we can say, all right, this one has a negative charge. And is more nucleophilic. All right, so it's pretty easy when we're comparing it across a row. The tricky thing is when we compare down a column. So let's make another list. We're going to compare nucleophilic atoms in the same column. Same column. All right. So let's make a little list going for this, but we're going to start off with this. Not as simple. Comparing in one column for nucleophiles is pretty complicated, actually. It depends on the solvent. So let's kind of change gears, and instead of talking about nucleophilicity right now, let's talk a little bit about solvent choice for substitution reactions. All right, do you guys remember the handout I gave you a few weeks ago, Common Solvents in Organic Chemistry? This is coming back into play. As you can see, we've got polar protic solvents. I'm going to even slide this up if I can. Where'd it go? Sorry, guys. It's kind of smush, but I'll fix it later. All right, polar protic solvent. What do you notice about all the polar protic solvents? They can H-bond. Perfect. All right, so in a chemistry lab, we have solvents that can H-bond. What do you notice about polar aprotic solvents? They just have a dipole-dipole interaction, right? They can't H-bond. We don't have any hydrogens coming off the phone, so to speak. So we can just say that these cannot H-bond. But they have a dipole. For nonpolar molecules, what do we notice about them? Yeah, really they have minimal dipole interactions. If you look at diethyl ether, you can say, well, there's a net dipole, but it's a really, really weak net dipole compared to something like acetone or acetonitrile. So these have little or no dipole. So the question now is, why are we bringing this up? Why do we care about solvents for substitution? This has a lot to do with the transition state of this reaction. So consider the transition state for SN1 and SN2. So let's make our little reaction coordinate diagram where we've got energy on this axis, reaction down here. We'll make a second one side by side. And let's do our SN2 reaction. What should this look like for the reaction coordinate diagram? Just one hump, right? So we'll go through our hump. We're going from starting materials to products. And if we were thinking about our transition state, we could say, all right, our nucleophile is approaching this carbon, and our leaving group is getting shoved off. And typically, we've got some substituents kind of hanging off of it. All right, and we'll put our double dagger around it. Let's do the same thing for SN1. What should this look like? Two humps, like the camel hump. So let's move this here. Let me clean this up. All right, and let's focus on the first transition state because that's the rate limiting step. So we said in this transition state, your leaving group is falling off, and then you've got these other R groups kind of nearby. And let's go back and add in our partial charges. All right, on the SN2 one, we said our nucleophile has a partial negative, our leaving group's got a partial negative, and then over here, our leaving group's partial negative, and our carbon's partial positive. So if we look at these transition states, we're going through pretty polar transition states, right? There's a big dipole in the transition state. Do you think a polar transition state prefers to be in a polar solvent or a non-polar solvent? Polar. Yeah, exactly. So if we're going through and looking at this, both reactions go through polar transition states, or polarized transition states, and they are stabilized in polar solvents. So do you think we're ever going to see an SN2 reaction being run in hexane? No. It's not energetically favorable. Instead, when you want to run an SN2 reaction, you want to use a polar solvent like acetone, something that will lower that activation energy by dropping that transition state down in energy level, right? So you can imagine there could be a hypothetical energy level that goes all the way up like that, but we're not interested in that higher energy reaction. We want to keep this as low as possible, so we want to stabilize that transition state, keep it reasonable. All right, so now what we've got to do, if we had time, would be to analyze aprotic versus protic solvents, but let's actually leave that for tomorrow. For your problem of the day, I would recommend using scratch paper or the back of the problem of the day to draw out the entire mechanism. I know I'm not going to grade you on that, but it's always good practice to draw out the full mechanism for each reaction. All right, and then tomorrow when we come back, we'll talk more about polar protic versus aprotic solvents. Yep. Mm-hmm.
remember